under slope ceilings, and I can say it's probably one of the most common questions that we actually get both in the US and when we're doing international work outside the US is, why can't I use a slope ceiling building? Or if I'm going to use a slope ceiling building, what requirements are available to me? So to start out, our general scenario that we're looking at is that a slope ceiling does not always mean any type of slope. So we actually start at a point of 2 and 12. So we go up 2 for every 12, we go horizontally. And it works out to be approximately a 9.5 degree angle. If we are at that level or lower, then we have realized through both field test and experimental data that the requirements work whether the ceiling is flat or up to that particular angle. So it's not until we reach a value higher than that that we need to start to worry about what type of criteria is available to us. Now in NFPA 13, there is a 30% increase when we deal with sloped applications and other types of occupancies. So that's part of the question that it comes across quite often as well is, okay, well, I'll just add 30% and that'll be good for storage too. And one of the things is that there isn't a tremendous amount of data on that. So it's not something that I've found anyone to be comfortable with saying, sure, use 30% and you're all set. So as we start to look at this little by little, we've tried to approach this in a way of, is there a way we can get to this information somewhat sooner? So how many sprinklers are going to open if there's a fire? If I stand here and tell you that 30% isn't the right number, then what is? How do we determine how many are actually going to be open? And then the second part is, where are those sprinklers actually going to be located? So if I have a fire, and will the sprinklers be directly over that fire? The common sense thing is that heat's going to rise. So if I put a steep slope on a roof, my heat's going to rise to wherever that peak is. If that peak is not directly over my fire, will I be opening sprinklers that are far away? So here's just a general layout that we used as we started to approach this question and think about, all right, is there a way that we can start to pose some type of solution? So you've got an elevation view on the left, and a plan view on the right, just showing the general concept that I just talked about. Heat's going to rise, so where does that mean it's really going to go? And you can see it rises up the slopes, at least that's the general thought. So if we looked at NFPA 13 right now, what are the options that are available to us? Well, we could start by just changing how the building's planned. So maybe we just don't design to have a slope. If you are from my part of the country where we don't burn couches on the weekend, Tom, we also get a lot of snow up there. So you'll find a lot of people don't want to have a flat roof to start with, because in the winter we can accumulate too much snow and it's a heavy load and changes how the structure has to be designed. So there are parts of the world and country that want to have a slope on their roof for reasons other than necessarily what's going inside of the building. And when we try to apply that to a storage occupancy, we now have to stop and think and say, well, I'm not supposed to have a slope with storage, so which side is going to win out for the design of this building? So one of the solutions has been is to take a building that maybe has this sloped roof and actually just put a drop ceiling on the inside. So we've made a flat ceiling as far as the storage and fire incident that we're considering is concerned. It does have to be a substantial ceiling, and we want to make sure it stays in place. You can't just put anything, you know, a paper film is not going to be appropriate. Our fire could burn through it kind of concept. And then the last piece that we talk about here is hiring a fire protection engineer. It may have a different label depending on where in the world you are, but it's hiring someone who's a specialist who can analyze the specifics of that particular building. So I heard Jerry talk about the client's perspective and what they were specifically looking for this afternoon. Well, that could be part of this. Maybe by bringing in a fire protection engineer that they can look not only at what hazard you're storing, but where it's specifically going and what minor modifications could be made to the plan in order to achieve the best fire protection at the best cost for the owner. So that's the third option that's currently on the table. Now we all know that when you start to bring in specialists, the dollars usually end up going up on the design for the building. So in order to start to approach a standardized method where we may be able to bring down the cost, we also started to put together a procedure of, well, if you are going to bring in that specialist, what are the things that they need to look at during this process in order to consider the analysis and what's going in there. So you have to think about the specific situation, and the end goal for us, because we're looking at this from the sprinkler side, is how many sprinklers are going to open and where are those sprinklers going to be located. And then tied into that is what heat release rate are we combating? What type of hazard and fuels do we have in the building? Because that will obviously change the answers to the first two questions. So you want to review any sort of existing fire tests that are out there, depending on what materials and arrangements you're dealing with. It may be something that's common, it may be something you can get access to, or it may be something that is a new arrangement or new materials. I know there's been a lot of talk about changing materials, in that about 30 to 50 years ago, we didn't see nearly the volume of plastic involved in commodities that we do today. As we start to move forward after seeing if there are other things that are comparable out there, we start to look for discharge criteria from those tests to see if we have necessary pressures with the sprinklers and what types of sprinklers were used. I know over the past 2 days there's been a lot of talk about different styles of sprinklers and different designs. So all of that comes into play with, well, which size orifice are we going to use for the sprinklers that we're putting into this particular scenario. Then you take the pressure, work with the angle, basically, in order to say, we know gravity has an effect. So how much water is really going to fall straight down? We apply a safety factor to that, because if we think about what happens in the field, it's not always our ideal scenario. What safety factor is used is going to be dependent on the specifics of the scenario and what that specialist really thinks is going on in that particular facility. And then also just applying that to the shape, and it becomes a little bit of a loop in that you have created this discharge criteria for a specific situation. If it's not agreeable to the owners and the authorities and so on, it may be a bit of an iterative loop where we go back and see how we can make this work for everyone on the same page. So once you think about how much goes into that specific scenario, we move to the next step of, is there a way to make a general approach? So in thinking about the modeling capabilities that are available to us right now, one method was to start with a CFD model, a fluid dynamics model that looks at each little cell of a space and how the heat transfers from one location to another. Because the models don't always represent the real world exactly as we'd like them to, we have to break them down as best we can. For the attempt that we looked at in this particular phase was to take these small steps. So we had used FDS, which is a computer program from NIST, and instead of being able to just put a straight slope in, we take these small steps over time. I should say over time, over the horizontal floor area. And we tried to make sure that they were small enough that based on the size fire we were going to have, it should have a low impact on the fire spread. So we worked with a company called Custom Spray Solutions, and we did, well, I should say we started this project in February of 2013. We're wrapping up the final report right now, and in hopes of, just like every other research project out there, that we continue with more research to make it even better. But what we did was we modeled double row racks that were 20 feet high and looked at the spray on the ceiling for its wetting surfaces, and it looked like something like this. And we started with just where is the water going. So if we're going to put a slope ceiling in, we looked at a flat ceiling, 2 and 12, 4 and 12, and 6 and 12 for these particular models. Once we were more or less comfortable with where the spray was going, and there was a lot of conversations about if the sprinklers themselves should be parallel to the floor or if they should be parallel to the slope, and what does that do to the spray pattern. So we looked at some of that as well, just in these spray models. And based on the ceiling itself, the steeper the slope got, the more of an obstruction it was. So our general conclusion was for a standardized protection of these storages that we really wanted to focus on a parallel to the slope installation for the sprinklers. But that didn't actually solve how many were going to open or how big the fire would be. So as we continued down this path, we looked at the size of the building. We made it a little bit smaller than we would have liked, just because of the computer capabilities and the time it takes in order to run these models. And we basically looked at a freebird, meaning we had locations of sprinklers in the model in order to get a feeling for when they would operate, but we didn't actually tell those models to discharge any water, just so that we could start to get a feel for opening patterns and where those sprinklers would be opening. It was Group A plastics as well, and this is what our model looked like. The yellow dots along the slopes are where those sprinkler locations were, and then the boxes are storage arrangement throughout the building. We used a standard heat release rate curve from FM on, we looked at both a Group A plastic as well as a Class 2 commodity. And those are your two curves. The fire itself was located in the middle of 4 sprinklers, and we had generic upright standard response sprinklers. So we were starting with sprinklers that we know a lot about. They're a type of sprinkler that's been through many tests, and it gives us at least some sort of baseline for comparing information. We did use 2 different RTIs. We used an RTI of 100 and an RTI of 300 to really kind of get a feel for the spectrum. When a sprinkler has many tests it has to pass, but there's no specific number on its response time index for the maximum values, but we felt that 100 was towards the lower end, where typical sprinklers are, and 300 would be towards a much higher end of where we see most products on the market. And then we did use a 74 degrees C activation temperature for the sprinklers. As I mentioned, there was no water flowing. So this is just loading in and showing you where the sprinklers were as they operated, and that they were, for the most part, relatively near the fire. Remember that once that first one opens, the rest of the data is an estimate, because we did not assume any water coming out of the sprinklers. So here is a comparison, and they're set to load in at the same time. So you see that the lower RTI is operating much faster than the higher RTI that we used in the model scenarios. The models were showing, though, that in general the sprinklers near the fire location were the ones that were opening. We were not opening sprinklers directly up the peak. So there's all of your locations loaded in. For the 6 and 12, we saw a similar concept, that they were the ones around the fire location itself, but they did move a little bit upslope in that arrangement, obviously a steeper angle than what we were looking at before. And then there's the the comparison of the slower and faster, again, it was exactly what we expected. The lower RTI was giving us faster operation of the sprinklers. But the patterns were not that dramatically different, as both of them are at the same slope in this example. And they've been giving me signs up here, so I'm going to load the dots in. So the general conclusions we had from that project was that up to a 4 and 12, there really wasn't a general change in the activation order based on the information from the model. The 6 and 12 still didn't seem too dramatic, but it was a little bit different than what we saw in the other examples. The RTI did make a difference, and that we think that there is a chance that we can get some slope ceiling requirements in the future. Obviously, we're not at the point yet where we have the specific numbers of what that criteria will be. So what are the next steps? Well, we need to look at some additional heat release races and as well as comparing them to fire size under flat ceiling situations. We also need to look at some additional modeling. There are other programs available. There are other ways to mimic a sloped ceiling within the programs. So there's a lot of information that's still ahead of us, but we do think that we'll eventually get there, and that it may not be too far in the future to start to get some standardized criteria. So with that, it's where we're heading. There's a couple options out there now, but hopefully it won't be that long. Thank you.